We will now look at a third recurrence equation. T of n is 4 times T of n by 2 plus n. We will again use the recursion tree method to solve this recurrence. So we start with a single node in the tree, T of n. In the next round, we expand the tree to one more level by replacing T of n by what appears on the right hand side of the recurrence. So we're going to write n in place of T of n with 4 children, each being T of n by 2. Then in the next round, we will expand each of these 4 nodes by using the recurrence for them and replacing them by the right hand side of those recurrences. So T of n by 2 is 4 times T of n by 4 plus n by 2. We get this by substituting n by 2 in place of n everywhere. So T of n by 2 is 4 times T of n by 2, the whole thing divided by 2, which is n by 4, plus n by 2. So when we open up these 4 nodes, we will replace each of these nodes with n by 2 and 4 children, each being T of n by 4. So T of n by 2 will get replaced by n by 2 with 4 children, each child being T of n by 4. The same holds for all the other 3, like for the other 3 children as well. So they will each have 4 children, each being T of n by 4. Then when we open up these nodes in the next round, T of n by 4 is given by 4 times T of n by 4 divided by 2, which is n by 8 plus n by 4. So all these nodes will get replaced by the cost of n by 4 and 4 children, each child being T of n by 8. So we can continue this process. Let me just illustrate that this node T of n by 4 is going to be replaced by n by 4 with 4 children, each child being T of n by 8. And we'll do this for every node here. So we're going to continue doing this, opening up the values of T up to lower and lower levels for lower and lower size subproblems until we end up at the bottommost level of the recursion tree when the size of the subproblem reduces to 1. That's when we stop. So at the very end, the recursion tree is going to look like this. We're going to have n at the top, 4 nodes with a cost of n by 2 each, 16 nodes with a cost of n by 4 each, 1 node with a cost of n, 4 nodes with a cost of n by 2. Each of them will have 4 children, each with a cost of n by 4. And then each of these will have 4 children, with a cost of n by 8, and so on, until at the very last level we get a cost of t of 1, which is some constant. So if we mark the levels of this tree, the topmost layer is level 0, the next layer is level 1, the next layer is level 2, the next layer is level 3, and so on. The last level is level h, which is the height of the tree, and if we look at level I, at level I, we are going to have nodes with a cost of n by 2 to the power I, because the cost of the nodes at each level are half the cost of the nodes at the previous level. So at level 1 we had a cost of n by 2, at level 2 we had a cost of n by 2 square, at level 3 we had a cost of n by 2 cube. So at level I we'll have a cost of n by 2 to the power I. And the number of nodes at each level is given by 1 at the first level, 1 at level 0, 4 at level 1, there are 4 nodes at level 1, there are 16 nodes at level 2. There will be 4 to the power 3 nodes at level 3, and so on. There will be 4 to the power I nodes at level I, and there will be 4 to the power h nodes at the bottommost level. And that's because if you look at the recurrence, whenever we open up a node to create the next level, we are creating 4 children. So the number of children at each level is 4 times the number of children at the number of nodes at the previous level. So the number of nodes at level I will be 4 times the number of nodes at level I minus 1. So the number of nodes increases by a factor of 4 every time we descend one level. So to calculate t of n, we have to calculate the level sums at each level and then add them up. So what's the level sum at level 0? It's just n because there is a single node with a cost of n. The level sum at level 1 will be 4 times n by 2 because there are 4 nodes with a cost of n by 2 each. So that's 2n. The level sum at level 2 will be 16 nodes, 4 square nodes, each with a cost of n by 4. That's 4n. At level 3, the number of nodes is 4 to the power 3, and the cost of each node is n by 8. So this is 64 divided by 8 times n, which is 8n. At the ith level, there are 4 to the power I nodes. Each node has a cost of n by 2 to the power I. So this will be n times 4 by 2, the whole thing to the power I. So that will be 2 to the power I multiplied by n. At the penultimate level, we will have a total cost of 4 to the power h minus 1, which is the number of nodes at level h minus 1, multiplied by the cost of each node, which is n divided by 2 to the power h minus 1. And that's going to be 2 to the power h minus 1 multiplied by n. And at the very last level, level h, we have 4 to the power h nodes. And the cost of each node here is t of 1. So we can write the running time t of n as the sum of these level sums from level 0 to level h. We'll write the term for level h separately, 4 to the power h times t of 1, because it contains this t of 1 term. And we can write the remaining h terms. Note that there are a total of h plus 1 level sums, because we start from level 0 and we go all the way up to level h. So there are a total of h plus 1 level sums. The very last of them is 4 to the power h times t of 1. And so the remaining h are going to be terms of the form 2 to the power I times n, where I varies from 0 to h minus 1. Now 4 to the power h, which is the number of nodes at the bottommost level, can be expressed in terms of n, because the height of the tree, h, is the height at which the size of the subproblem reduces to 1. When we create the first level, the subproblem size at the first level was n by 2. When we created the second level, the size of the subproblem at the second level was n by 2 square. So when we created level I, the size of the subproblem there was n by 2 to the power I. When we create level h, the size of the subproblem at level h is theoretically n divided by 2 to the power h. But we know that h is the height of this tree, that is, it is the depth at which the size of the subproblem reduces to 1. So equating n by 2 to the power h to 1, we can calculate the value of h in terms of n. It's going to be log of n base 2. So if we substitute this value of h over here, we get t of n is 4 to the power log of n base 2 multiplied by t of 1, plus we can take n out of this summation, so that becomes n times sigma of I varying from 0 to h minus 1, 2 to the power I. Now this term, 4 to the power log of n base 2, is equal to n to the power log of 4 base 2. We can exchange 4 and n, and the value will remain the same. So this becomes n to the power log of 4 base 2, which is n squared. So t of n is n squared times t of 1 plus n times the sum of h terms. The first term is 1. At I equal to 0, we have 2 to the power 0, which is 1. The second term is 2. Third term is 2 square, and so on. And the last term is 2 to the power h minus 1. So we have h terms in this series. And if you note, this series is again a geometric series. But this time it's an increasing geometric series, because the value of the common ratio is 2. So r is equal to 2. Each term is obtained from the previous term by multiplying the previous term by 2. and the first term is 1. If you recall, we had derived a formula for the sum of k terms in a geometric series. So S, which is a plus ar square and so on till ar to the power k minus 1, is given by a times r to the power k minus 1 divided by r minus 1. And we write the formula this way when the value of the common ratio r is greater than 1. Otherwise we write it as a times 1 minus r to the power k divided by 1 minus r. So in this case the value of the common ratio is 2. So r to the power k minus 1 and r minus 1 will be positive. So if we use this formula, the value of this summation is going to be 1 multiplied by 2 to the power h minus 1 divided by 2 minus 1. There are h terms in the series. The first term is 1 and the value of the common ratio r is 2. So this simplifies to 2 to the power h minus 1. Now 2 to the power h is 2 to the power log of n base 2 because we calculated h to be log of n base 2. So this simplifies to n minus 1 because 2 to the power log of n base 2 is just n. So S, or the summation, is equal to n minus 1. So T of n is n square times T of 1 plus n times the value of this summation, which is n minus 1. And you can see that this is a quadratic expression, and so T of n is going to be n theta of n square. This was a different type of recurrence from the two earlier examples we saw, because in this example we obtained a geometric series that was increasing down the tree. In the previous problem we encountered a geometric series that was decreasing down the tree, and in the first example we took, we saw that the values of the level sums were same throughout the tree. So there are three different cases. The first case we looked at was when the level sums are exactly the same at every level. In the second example we took, the level sums were geometrically decreasing down the tree. And in this example, the level sums are geometrically increasing down the tree. Now, when the level sums geometrically increase down the tree, you can see that the overall asymptotic complexity of T of n is also the asymptotic complexity of the very last level sum, or the very last term in the geometric series. For example, let's look at the value of this term, 2 to the power h minus 1 multiplied by n. What's that equal to? So the cost, or the level sum at level h minus 1 is 2 to the power h minus 1 times n. This is nothing but half of 2 to the power h times n. Now 2 to the power h is n because h is log of n base 2. So 2 to the power h is nothing but n, and so this is nothing but n square by 2. The level sum at level h minus 1 is n square by 2. The level sum at level h will be, we actually calculated that, that was 4 to the power h times t of 1. 4 to the power h is n square, and so that's n square times t of 1. So n squared times some constant t of 1. And the overall value of t of n was theta of n squared. Now this is also in theta of n squared, this is also in theta of n squared. So the level sums at the last level and in the penultimate level already have the same asymptotic complexity as the overall running time. But if you look at the first level, or the zeroth level, the level sum at the zeroth level is simply n. So you can see that it's the very last level sum in this increasing geometric series that is asymptotically most dominant, and it essentially determines the overall asymptotic complexity of t of n. In the previous example we saw where we had a decreasing geometric series, the overall asymptotic complexity of t of n was determined by the asymptotic complexity of the first level sum, or the first term in the series. So this is something to note. When you have an increasing geometric series, it's the very last term that's going to determine your overall asymptotic complexity. Actually, you can think of the very last term here, 4 to the power h times t of 1, as really part of this geometric series, even though we wrote it separately. The reason we wrote it separately was because this t of 1 does not neatly fit into this geometric series. But if you look at the form of this term, you can see that each term in this geometric series has a power of 4, which is steadily increasing down the tree. And in fact, for the last term, it's a natural continuation of the previous term. So the previous term was 4 to the power h minus 1, and at the last term we have 4 to the power h. And if you look at the second part of the term, these are the costs for the individual nodes. These are decreasing by a factor of 2 down the tree. At the very last level, at the penultimate level, the cost of each node is going to be equal to 2. If you calculate what n by 2 to the power h minus 1 is, that's going to turn out to be, let's do that, n by 2 to the power h minus 1 is going to be n divided by half of 2 to the power h, which is 2n divided by 2 to the power h. 2 to the power h is n, and so this is equal to 2. So the cost of each node is going down by a factor of 2 at every level, and at the penultimate level it is exactly equal to 2. So there are 4 to the power h minus 1 terms, each with a cost of 2 at the penultimate level. Then at the very last level, the number of nodes increases again by a factor of 4, so it becomes 4 to the power h. And the cost becomes t of 1. Ordinarily it would have become half of 2, which is equal to 1. But instead of 1 we have t of 1. So had it been exactly equal to 1, we would have accommodated this term conveniently within this geometric series. But even if t of 1 is not exactly equal to 1, we can still think of it as approximately part of this series itself. So conceptually speaking, you can think of this term as also being a part of the geometric series. And so if you look at the asymptotic complexity of this term, you can get an idea of what the asymptotic complexity for the overall running time is. Or you could look at the penultimate level. The asymptotic complexities here are going to be the same. But at the very first term, it's going to be different. So for an increasing geometric series, you have to look at the terms at the very end. Those are going to be the largest terms, and those will determine the overall asymptotic complexity of t of n.